This video will introduce you to PID controllers. To start with, we're going to review feedback controllers from last lecture. Then we're going to explain the limitations of the proportional controller we talked about last lecture. And then we're going to introduce PID control as a solution. So, feedback controllers. Recall that feedback controllers take in a desired input to the system. This is any set point you want, any number that you want to give it that the system can actually reach. Usually in robotics this is a position or an angle or something along those lines. The system knows the actual position of this value based on where it is in the real world, what its sensors tell it, and so you can take the desired minus the actual, that's the error, feed that into the controller, which then gets fed into the system, which tries to actuate that as much as possible. The sensor then gives an updated actual position, so the controller has a new error to work on, and so on until you reach your desired state. So let's imagine that you're flying a helicopter. You're flying a long level flight just great, and you get to a spot and you say, I want to climb 100 meters. So let's put this in controls terms. You want to climb 100 meters, that means your error right now is 100 meters. So what does this mean for control? Well, you're an experienced helicopter pilot, so you decide that this means, based on your proportional controller, that you want to have a collective of 30%. Collective is what makes the helicopter go up. So you apply a 30% collective, you wait a little bit of time, and eventually you're about halfway there, 50 meters error. You say, okay, I can ease up on the collective a little bit. I want to hit exactly 100 meters and not overshoot, so I'm going to make it 15%. Because we're at half the error we were before, so we'll do half the collective, just like a good proportional controller. We go on for a little bit more. We have the error again, get to 25 meters, and say, sure, we'll go ahead and reduce it a little bit more. This goes on and on. We'll skip a few steps here, and eventually you get to the point where you're 0 meters error, 100 meters altitude, and your collective is 0% because you're at the right spot. This is great. Everything went as planned. What could go wrong? Well, what happens if there's any other perturbations to the system? What happens if there's any downdraft, any wind, anything else? See what happens with just a downdraft. So the downdraft is just force pushing you down as you're flying along. So you're flying along, getting a little bit lower over time. You decide you want to climb 100 meters, like we discussed before. You apply the same proportional controller as before, and you set your collective to 30%. So you fly up a bit, but not quite as high as last time. Your error right now is 55 meters. So what do? Well, you put this in the same equation you used before, and you get out that you should apply 16.5% collective. So you do this, and you keep iterating and iterating along again, and eventually you get to the spot where you're really close to where you want to be. You're 5 meters away. But your control algorithm is telling you to only put in 1.5% collective at this point. That's never going to overcome the force of the downdraft. So clearly we need something else here. Let's think about this. This is the graph of roughly what it looks like without a downdraft. So we fly up pretty quickly to 50 meters. We start to go a little bit slower to 25 and then slower and slower until we get to 100 meters and we're happy and stay put. With the downdraft, the curve looks pretty much the same, except we have this 5 meter error at the very end. So why don't we just tune the system again? Why not just tune it to work with the downdraft? Well, this works great when the downdraft is the same. We can get the system perfectly like it was without a downdraft at all. But what happens if there's any sort of different wind, different downdraft, any other perturbations? Well, things could change. So you could oscillate around your point, never quite reaching it. You could go unstable and start oscillating much more around it. After every iteration, you could end up maybe 5 meters higher, 10 meters lower. It's difficult to say. So clearly we need more than just one knob to tune in this. We can't just rely on the proportional control. There must be other gains we can set. So let's look at a graph here and talk about some terms that we're going to need as we're going forward in this lecture. So first off, you have to have some concept of how fast your system is getting towards the state you want it to be in. So we call that rise time, and that's generally defined as the time it takes to go from 10% to 90% of your final value. Your final value we typically call steady state. It's that straight flat line at the end there that just keeps going on forever, about like that. Now, a lot of times you're going to go past your desired value and have to come back around. We call that overshoot. And overshoot is a percentage you go past the desired until you have to come back around. Finally, you notice at the end here that the actual value, the orange line, isn't quite at the desired value, the blue line. And that error that we call at the end is the steady state error. That's what we saw with the helicopter with the downdraft, and that's what we're trying to fix, along with maybe minimizing overshoot, minimizing rise time, and so on. So what does this mean? What are we looking for? We're looking for something that responds to error. We're also looking for something that reduces the steady state error in the end, and something that reduces the overshoot and settling time, the time it takes to get to the steady state at the end. So what can we do here? Well, we already know that proportional control responds to error pretty well. Wasn't quite sufficient, but we know it responds to it well enough that we can call that box checked. So how about steady state error? If we start accumulating the error, then we'll eventually get a big number that will push us towards converging with our desired point. So how do we do that? We can integrate. We integrate the error over time, and this gives us a value that we can use to control ourselves to reduce the steady state error. The last thing is reducing overshoot and settling time. It turns out if you look at the slope of the error, if you look at the change of the error over time, then you can, and try to minimize that to 0, then you can reduce the overshoot and reduce the settling time. So we can do that by playing with derivatives. So proportional integral derivative, PID control. Let's go back to our previous conception of a feedback controller. All we're doing here is taking this controller box and expanding it. And we're saying within the controller, we now have a proportional component, an integral component, and a derivative component. Proportional component takes a gain, Kp, times the error, just like we were doing before. The integral component also takes a gain, Ki, and multiplies it by the integral of the error over time. And the derivative component takes another gain, Kd, and multiplies it by the derivative of the error, so basically the difference between the last couple of time steps. All of these take in the same error that we were using before for Kp, and they do different math to it to get an answer at the end. And each of these components is added together in the end to produce the input for your system. And if you want this in math terms, the output control is Kp times the error plus Ki times the integral of the error plus Kd times the derivative of the error. So this gives us 3 knobs to turn, Kp, Ki, and Kd. Let's review. Proportional controllers can't handle all the major disturbances or steady state errors that we see in real-world systems like robotics. PID controllers allow you to tune the proportional to decrease the rise time, the integral to decrease the steady state error, and the derivative to decrease the overshoot or settling time. Next time, we're going to talk about how to tune this PID controller.